Hi, everyone. This is ET350 Lecture 4. Today, we're going to cover DC machines. We're going to look at how it operates as a generator and without and with the commutator. We'll look at also how it operates as a motor, and then we'll talk about a specific one. This is the separately excited version. We'll look at the armature and field coils, and then two very useful equations that relate the torque to the current and the voltage induced to the speed. These actually are from Bill's law or the Lorentz force and Faraday's law. Okay, so let's begin. So a generator without a commutator actually produces AC voltage, okay? And when we add a commutator, we actually rectify that voltage. It's not perfectly smooth, but it is rectified. So it is now DC, okay? Kind of a counterintuitive result, but that is the case. Without a commutator, we get AC voltage. Now, for when we look at a motor, there's going to be many types. There's going to be series, there's going to be shunt. But in this lecture, we're going to look at separately excited. What do we mean by separately excited? We mean by where we're going to get the magnetic field. And there's two ways. One is either using a permanent magnet inside your motor or generator, it's the same device, or externally exciting it using field coils, okay? And so that would require field windings and another source, okay? And so we'll look at a separately excited version today. Shunt and parallel wound, as I mentioned, are another version. Universal or series wound is another version. And there's also the compound parallel and series combination, but this is the one we'll focus on. So let's look at this first, this generator without a commutator. All right. So here's a simple drawing, very, very simple drawing. You have a magnet, or two magnets, a north and south. So that means by our convention, the magnetic field is going from the north face to the south face as drawn here. Now, what I have drawn, you got to be careful to think about how this is going, is I have an armature coil. Right now, I'm only showing one loop, but you can imagine there's a lot of loops. And I have two terminals. And let's imagine I'm measuring the voltage here with my red lead at the positive and the black lead at the negative. So it's like I have a multimeter and I'm doing this. Okay, now I have a handle here, and so this dashed line represents the axis of rotation, so I could spin this, right? And so here's an example, like here's an armature. This is magnet wire, and for your projects, you will be using this. Notice it seems like it's actually bare copper, but it's not. It actually has a very thin layer of insulation, so that way when this wire goes in here, it doesn't just short, it actually doesn't touch the other side, right? And then it goes around and around, comes out. So that would be equivalent to like this, and then it would spin around and around. Now, yes, if this was a physical system that we implemented, sure, the wires would get twisted, right? But just imagine we can measure this voltage using some multimeter, and I can spin this like using an external mechanical energy, right? What we're going to look at today is, well, what would that measurement look like? What would that voltage induced look like? What would the current look like? Which directions are they going to be? Okay. Okay, so to look at that voltage, we use one of the 7 fundamentals, right? We have what, the 4 Maxwell equations, we have the Lorentz force with the cube, and we have the definition of flux, and we also have the convention north to south, right? Okay, so one of the 7, the Maxwell equation, the fourth one here, Faraday's law, V induced equals N d phi dt. And from our last lecture, we kind of said we're very loose with that sign. I'm just going to ignore that Lenz's law sign, but we know we're setting it up in a way where V induced is in such a way that it opposes the d phi dt. Well, how is this d phi dt created? Well, it's created by me literally spinning this handle, right? That's how I'm getting a flux change in this area. Remember, flux is defined as this, BA cosine theta, again, one of the 7 fundamentals. So if we look at here, we have an area vector, good, and a V vector. And let's look at what's changing and what's not changing. Well, if I have a constant magnetic field, either this is generated by a permanent magnet or field coils, we'll assume this V is constant. Let's say this A is unchanging. So I keep the same surface area inside here. So I'm not changing that, right? So the actual magnitude of this cross-sectional area doesn't change. However, the orientation theta, if I'm spinning this relative to B, So is changing. So this A and B is actually changing its angle. And so if I were to take the time derivative of this guy, I would get this expression BA. And if I take the time derivative of the cosine, I can pull it out and I get omega or theta dot, okay, times sine of theta, right? Let's ignore all the signs for now. Let's just get the absolute value. And so d phi dt is what's going to go in here. And so that means my V induced is going to be n, the number of turns. So you can see there's a lot of turns here. Yes, I've only drawn one here, but there's a lot of turns there, times this guy, BA omega sine theta. What is this telling us? This tells us that this voltage induced that we're going to measure on the multimeter is dependent on all these constant terms. And let's say I'm spinning it at a constant rate. That means omega would be constant if I'm constantly turning it. However, this is changing. Sine of the angle is changing. And we know how sine of the angle changes, right? Because as you spin, theta is going to be changing inside the sine term. And that would look like this. So that means the overall V induced, if I'm spinning, is actually generating AC, alternating current, right? Alternating voltage, right? You see this here. So I'm going to be seeing positive, negative as I'm spinning this through, all right? All right. These points here, notice there are going to be points during the rotation where I'm actually generating zero voltage. We'll call those the neutral points, okay? But you're going to go 0 to max positive to 0 to max negative, 0 to max positive, 0 to max negative as you spin this through. Kind of, like I said, a counterintuitive result that a DC generator without a commutator, no commutator, actually generates AC. Another bit of terminology just to remind ourselves, this Faraday's law voltage is what we call in the street the back EMF, okay? This is the back voltage that's generated, okay? So in a generator situation, as I'm spinning this, this is the useful voltage, the useful electrical energy that's coming out. Now, if it's alternating like this, maybe it's not as useful for a DC application, but let's keep going further. And what I also want to look at is the forces on here, okay? Okay, so for this system, what I'm feeling is also not constant. I'm not feeling a constant torque. I'm actually going to feel a kind of a jerky torque. In fact, that force is going to follow the sinusoidal wave. And so what I want to do now is kind of break it down into 4 images of different points of the rotation as I'm going through here. So what I have in my next drawing, now I'm warning you the next few figures here are a little bit busy. But what I have here is I'm looking down this handle and I'm looking at these 2 wires here, okay? Because these are the 2 main wires that matter, right? And what I have is I have an X to show that if current is going into the page or a dot to show that current is induced and coming out of the page, right? And the idea is as I'm rotating through counterclockwise, I'm going to have orientations where I'm going to feel the maximum force resisting me, right? Because remember, if I'm moving this, I'm like the generator, I'm the prime mover on a generator. I better feel some resistance. I don't get energy for free, right? And so we can set that up. So let's look at the first figure here. So in this, I know, like I said, it's a very busy slide, but let's just kind of parse out what's going on. North, south, good. I'm in this orientation, we'll say theta is 0 at the top orientation. Notice I put a little star to denote this top line that's going to the negative terminal here. Okay, so I have a star, and as I rotate through, you'll see the star rotate. I have my handle, I'm rotating through here, so you can see my velocity that I'm going through is dictated by these arrows. Now, if this is a generator situation, I'm gonna feel an opposing force, right? That's actually from the Lenz's law, Faraday's law behavior. It doesn't like a change, okay? So I'm putting a force in the opposite direction of velocity. It's resisting my motion, okay? B is going from north to south, very good. And this is the point of rotation, okay? So let's think about what's happening in this case. In this case, notice B and the force opposed are aligned. They're in the same direction. Either they're totally in the same direction or they're totally in opposite direction. And we remember from Bill's law in that cross product, or that Lorentz force, is to get the maximum amount of force, we need the current or all these things to be orthogonal or perpendicular to each other? Because they're aligned, even though the force vector should be in this direction, it'll be 0 in magnitude in this specific 0-degree orientation. And I wrote that here. F and B are parallel, so Bill's law can't induce an I, and no force opposed exists, therefore no I is induced, okay? So this is a situation where if I'm at the top, just in this little thing here, rotating like this, just at that top, no force induced, no current induced, and 0 voltage induced. So I'm here, right? No voltage induced. Now, as I rotate through, now what's going to happen is these two lines, so these two lines, remember, these two lines are going to cut these flux lines in a perpendicular fashion. And what happens is now the force opposed is going to be pointing up. Okay, and so let's look at that in the next page. And so you can see as I've rotated through here, and now the velocity is still, angular velocity still wants to be in this counterclockwise fashion. And look at the force opposed. I made it opposite, right? It's always going to be opposite if it does exist. And now look, B and F are now perpendicular, and I have an I induced that's going to support this F opposed to fight the change, right? And so let's use the Bill's law. F, B, and I is going to be pointing up out of the page. On this side here, if F opposes down, okay, F opposes down, let's look at what's going on. F is this way, and then B is to the right, I is going into the page. Does that, I hope that makes sense, right? And so in this orientation, remember I'm spinning this through, but if I just kind of freeze frame right here, this is the orientation in this kind of region where I'm going to get the most feeling of force resistance, like, oh, okay, I feel a little bit of resistance there, and I'm going to generate the most voltage here, okay? And so you can see that this current is actually coming up towards me, so it's going this way, right? And it's going down and it's going into that positive terminal, generating a positive voltage, okay? So this is where I'm going to get the max voltage and the max current and the max force opposed, all right? And this is at that angle where the area is this way, okay, good. Now, as I keep rotating, we're going to kind of get back to this orientation. Notice the star here. The star's here, then it's here, and then the next point is going to be down here on the bottom, but it's going to be looking very much like this one. So theta was 0, 90, and then we'll get up to 180 here. And so we can see the star is on the bottom. At this point, it's very similar to this one. Force opposed goes to 0 again because the B and the F are aligned. Therefore, Bill's law can't induce any current that's going to help oppose that situation. So everything goes back to 0. So we're down here at this other neutral point. Okay. And then we're going to go to 270. So again, we're going to keep rotating. Now the star went from here to here to here, and now it's over here. And so you can see that we're in a similar situation as this one, where the force opposed again is still opposite, but we are now inducing the most amount of current and voltage again, right? And we can use our Bill's law. Notice the same thing. If the force opposed is opposing the motion, we still have current coming up out of the page. You can see that there. Or here on this side, we have current going. So let me get everything correct. B going to the right, F going down, and current going into the page, all right? Now, notice what's happening, though, is that the sign flips. Remember, this star is actually this top part, okay? And so now we've rotated 270 degrees, and what we're saying is current is going into that top part, or into where that negative terminal is. So you're building positive charge on that negative terminal. We're going to be generating negative voltage, if that makes sense, okay? And so, yes, I induces max, V induces max, but note the change in direction of the voltage and current. Okay, so I hope this gives you some intuition as to how a single coil or a very simple DC generator without a commutator, as it rotates, actually generates AC voltage, AC forces, AC current. And what can we do? We can add a commutator, right? Okay, so let's go to the next slide here. So what does a commutator look like? Well, I'm going to move this one actually out of the way so we can still look at the original one. So a commutator might look like something like this, all right? So imagine two copper ends So instead of I'm just measuring B induced directly, 2 copper ends are soldered directly to these wires. And this commutator can rotate, but now you have 2 carbon brushes that are fixed. And then I'm measuring the voltage here, okay? And so here's a zoomed in view of what I'm talking about. You have 2 commutator sections. You have an insulation section separating these 2 electrically, and you have these brushes. The brushes do not rotate, but the commutator does, okay? And the reason why they use carbon brushes is so that you don't weld your conductive material to the copper commutator. And here's a physical commutator right here. So it's kind of hard to see, but let's see, here, this is better. This is a commutator section right here. And let me get my flashlight out. Maybe that'll help. Okay, so let's see here. Yeah, there we go. Now we can see it better. So you have those copper commutator section. Now you see a lot of commutator sections in this design, right? Whereas in the other one, you don't see as many. We're just dealing with a simple case where there's just 2. And then you have the 2 brushes. There you go. You can see it's going to be right down there. Okay, right down there. I know it's hard to see. Sorry for the light. But you can see a spring-loaded brush. I wonder if I can actually take out the brush. Let's see, does that pop out nicely? Maybe it doesn't pop out nicely. But you can imagine this would be a maintenance item, right? So brushes wear out, and this is something that would need to be replaced, and maybe you might have to shape it so that it conforms to that face. See how you might have to grind a nice round face in there. Okay, so what would happen? What would happen is this. Here's your original AC current and voltage, right? And with the commutator, it's going to rectify it, right? Just like a diode. Remember in 370, we learned about diodes, how they rectify? Well, this is like a mechanical diode, right? It's going to mechanically rectify. Really cool, right? This is technology that still is in place, and it's technology that worked before we were able to develop transistors reliably. So pretty cool stuff, how creative our forefathers were, right? Okay, let's keep going through here. Okay. So you can imagine, if we're going to be building these for your motors, the orientation, all this stuff matters, right? Do I put the brushes here? Do I put the brushes here? Do I have my how do I have my insulation relative to my brushes? What about the orientation of the magnets? Yes, all that matters. You have to take into account everything, because if you get these 90 degrees off or something wrong, you're not going to generate voltage, or if you're running it as a motor, you're not going to get this thing to spin, right? Because you can see here that there's an orientation where in this specific orientation, you can see how this brush section is actually touching both ends of the commutator. So you actually have shorted everything across. If it rotates a little bit, now this section would maybe touch this part and this section would only touch that part. But you got to be careful how you orient everything so that you can have it behave nicely as a generator or motor. So let's look at some good and bad orientations. Okay, so let's look at a good orientation. Now remember the neutral position. The neutral position, if we go back to this one, is in this actually orientation as drawn. See how the armature wires are not next to the magnets? That's a neutral position here. This is where we were not generating a lot of current and voltage, right? And so you can imagine that's an okay situation to have the insulation touch both of the brushes, right? Because it doesn't matter if it's short. If I'm not putting any current or voltage across or through these, it doesn't matter. So this would be a good orientation. Now let's maintain this orientation and let's rotate our commutator and wires 90 degrees, right? Remember the brushes stay constant, and you can see that the line now is vertical, and you can see now I have a nice electrical separation. And remember, this is the orientation where you're getting max current and voltage induced. And yes, now that insulation section is separating the 2 commutation, and I get the max amount of voltage induced outside my brushes. So this is nice, okay? This would be a good orientation. Now let's look at an example of a bad one. So a bad one would be like this. Here, notice the only difference is I'm starting in the neutral position, right? I have the wires on the top, but notice how all I did was accidentally install the commutator 90 degrees off. In this case, yes, the commutator is electric, or the brushes are electrically separated, fine, but you're not generating any current anyway, so there's no point doing this, okay? Now let's rotate this bad section 90 degrees. This is a real problem, because now when I'm rotated down over here, you guys remember, we're generating the most current and voltage, and what happens? Well, if I get the most current voltage from A to B here on both ends of these commutator sections, I've now shorted it across, right? I'm just burning energy, right? No, and I'm not even getting any voltage out of here, which is my desire if it's a generator application. So it's a very subtle change, right? And so when you guys are designing your motors and generators, this is something you got to be aware of, all right? So you might have to pause this video, rewind, come back, but I hope you see the subtle difference between this and this, okay? All right, let's keep going. Now, you saw that in this physical example here, there's a bunch of sections. Well, there's a reason for that. They want to make the voltage induced smoother, right? So you add more commutator sections and more coils, right? Or I mean, the other thing you could also do is add a capacitor on the end. And in fact, boom, there's a capacitor right there. If you can't see it, right? This is the capacitor. So they're doing both. They're adding capacitors and they're adding more commutator sections and more coils. And so a drawing might look like this. I got my two brushes here. I have more commutator sections and I have more coils, right? And so the voltage, while not perfectly smooth, becomes smoother, right? So it's kind of like, remember we were talking about in 370, we had the half rectifier and then we have a full bridge rectifier, right? And so this adds more rectification and you can get it smoother so your capacitor has to do less work. Pretty, makes sense, Okay, let's move on to a DC motor application because you guys will all be building motors. And the nice thing, it's the same configuration as a generator. You still want to make sure that you're accounting for this good coil commutator brush orientation. If you don't do that, the motor won't work. Okay, let's keep going. What you're doing instead is you're connecting a voltage source to the armature coils. So now instead of this as like an output, I'm measuring voltage or taking that and making a light bulb turn on, I'm now applying a voltage to this and making this guy spin. So no longer is something manually spinning, some prime mover manually spinning it. It's, I want it to spin by my own electrical energy that I'm going to provide to it. What will happen is current will flow and forces and torques will be created by Bill's law, okay? And let's look at a drawing of one, okay? And so here's a nice drawing of one. So let's go through this a little slowly. We have a north and south side, okay? And you can either generate that north and south side via permanent magnets or field coils, okay? You have to generate a magnetic field somehow, but these are two ways. So how do you generate a magnetic field using field coils? Well, you can run coils around the outside. These are on the stator, stationary, not moving, and you can apply current to them. And by Ampere's law, you can make sure that the current is running all in the same direction. So let's look at this one. If I want this side to be the north, I would want, depending on how I've wound my coils, I would want current to flow this way. Yes, Ampere's law shows north side magnetic fields going this way. Now, what about on this side? I would want, again, Ampere's law to make the flux density go left to right, if this is my intended flux density direction, okay? All right, so these are your field coils, or they can be permanent magnets, right? Either or. Okay, now I have my armature coils, right? These are the things that go spinny, spinny. Same with the commutator, right? These, I didn't draw this in the center just so that it's more visual, but this would be aligned along the center and this would spin. And so let's say I had my brushes here attached to a voltage supply. And so if I apply voltage to here, let's imagine what's going to happen. Current is going to flow, we'll call this current IA for armature. It's going to flow through the brush into this section of the commutator into the left side, back around, and then coming back out the right side through the commutator, back to the brush and back to the voltage supply. If I use my Bill's law, I go, okay, well, if I don't look at the force yet, if I have B and I, let's go see what's happening. I is going in the page, B is going this way, force is going down. Yes, that's good. It's going to create a torque in this counterclockwise direction. And if current is coming up out of the page, B is still going to the right. So let's get that orientation. Force is going up. Very good. So this is going to create a counterclockwise torque and have it spin in the direction shown. This is a motor situation, not a generator situation. Okay. We'll use the term VS for voltage source, or sometimes VT is used, maybe in your homeworks. Okay. But I hope you can see what's going on. And then as this spins, imagine this is going to keep spinning, keep spinning, keep spinning, and this is going to flip, right? And why does it flip? Because now this wire is going to be over here. But the nice thing is this flips the current, right? Because you're flipping the wire, but you also need to flip the current, and that's what this enables to do. So this can keep going, right? If you were just applying voltage straight to here, what would happen is it would spin and then it would just lock, because then the second it went here, it would generate a force that would bring it back. Okay, so this is what allows it to keep moving, right? And you will have to figure that out, because you're probably going to have multiple armature wires in your design, and you want to have it oriented in such a way that it keeps spinning and doesn't just spin and then lock, right? Okay, so let's keep moving here. So the next few slides are kind of showing how do we model this a little more theoretically. And the reason why we do that is not to confuse you. What we want to do is bring in some of those 7 fundamentals and use it as tools to be able to describe and model and understand this stuff in our head, right? If you're getting confused, of course, rewind the video, ask me in class, right? But there's going to be a little bit of circuitry stuff and some equations, but I'm hoping they all rely on your 250 understanding and the 7 fundamentals that we've gone over. Okay, so let's look at the armature circuit. So the armature circuit is this guy, right? This is the armature. And so we have a voltage supply here. These are wires, so, you know, just like this. So they're going to have some internal resistance. So we'll model that with RA. And then current, IA, is flowing through everything. And now remember, even though it is a motor, or we want to operate as a motor, as we spin, you can't get away from the fact that we have Faraday's law still employed. And it's still going to produce that back EMF, that V induced, right? And that is represented by this EA. And notice I have the sign of EA in such a way that it is fighting, this positive terminal is fighting IA. And let me just back up. Where's that EA coming from? It is coming from this Faraday's law. It's the same thing that is governing this one when it's a pure generator. So it is a unfortunate thing that when you want to run it as a motor, you still generate, you know, this voltage. It's a voltage that's smaller than this under normal motoring circumstances in such a way that current flows, but it's there nonetheless, right? You cannot make that go away. That's just, it is what it is. That's just part of the nature of it, okay? Now, this EA, as your speed picks up more and more, you are going to get more voltage, right? And we saw that, of course, in the Faraday's law equation, right? Right here, more speed, more voltage, okay? So this is your simple circuit model. And here are all the terms. The VS, of course, voltage source. RA is the armature resistance, armature current, back EMF, right? Faraday's law induced, good. And on the mechanical side, well, what are we generating? Mechanical energy. Torque and speed. Remember, torque and speed is power. And what are the units for these guys, everyone? Radians per second. We're not using degrees per second. We're not using RPM. Radians per second, because power equals torque times speed, or angular velocity in radians per second. Okay, good. Another small but subtle point I want you to note is that this, I put DEV for developed. And this is an ideal torque, okay? There's going to be an actual torque out, which accounts for the frictional losses, but this is just the ideal. The reason why we bring up this ideal torque and speed is because this is the bridge that's going to connect the electrical energy, IAEA, to the mechanical energy torque dev omega m, right? M for motor, all right? So remember, power is being converted from an electrical version to a mechanical version, right? This is the electrical bridge. This power IA or IAEA is equal to torque dev omega m. So that's the nice bridge right there. Okay. Now I'm going to push this to the side and let's look again at this. Let's look at the field coil circuit. Well, if we're a permanent magnet, we could ignore the field coil circuit because it's just run by the magnets. But if you do have a field coil, you would have an external voltage and you would have the armature winding. So you would have this simple circuit, right? Some VF, you'd have some IF going in here, some IF. And again, if it's a coil, you model it by some resistor and inductor, okay? If it's field coils, if it's direct current or steady state current, like this is just a DC steady state current applied to these, remember from ET250 that the voltage across an inductor is actually 0 if there's no change in it, okay? So really, you are just burning off energy in this resistor, okay? So the field resistance is modeling the resistance in these wires. So yeah, that is just, you know, a cost you have to pay. It hurts your efficiency, but it is what it is if you excite it. Now, why would you want to go with separately excited field coils over a permanent magnet? Well, the reason might be is that I potentially could get a stronger magnetic field using a field coil than a permanent magnet. Because if I just keep increasing the current, I would get a stronger and stronger flux density. The other reason might be cost. It might be cheaper to just add some copper, right, than to buy expensive neodymium magnets. So there's a few reasons why you might go down this route of field coils, okay? And so these are all the terms. Okay. So let's look at some properties for this separately excited situation. IF and IA are independent and makes sense, separately excited, two different circuits, right? IF and this current IA are independent. VF, the voltage that would control this field current, can be very independently of this VS or VT. So if I want to get more flux density, I could just turn up this guy, right? Okay, what else? For a permanent magnet, no VF is required. Nice. Okay, so that's actually could be a benefit as well for going for permanent magnets. The permanent magnet can be small and light. Here's a cute little motor that is a DC motor, and there's two little baby permanent magnets in here. And the two terminals are, I mean, you can't see it here, but there's one there and one there, and this is a permanent magnet DC motor, okay? So lighter, smaller, lighter, as you saw, no extra coils or iron. Now the problem is with permanent magnets, you can demagnetize due to heat, right? Heat is always a killer in engineering, and definitely no exception here with these motors. And like I said, only a limited flux density can be developed. Okay. Now I'm going to go over two useful equations, and the first one is going to be torque developed equals K phi IA. And you're looking at this and you're like, well, what the heck? What is this? Torque developed equals K phi IA. Well, what is the torque developed? It's the mechanical torque. We talked about that before, and it is directly proportional to the current and the flux. All right, so, but where does this come from? Remember the 7? We had flux density, definition of flux. We had the Lorentz force. That's the one that creates this one, right? The developed torque is proportional to the magnetic flux and armature current, right? So why Bill's law? Remember Bill's law, F equals BIL? Well, force is directly related to torque. You just need to get that lever arm, right? B, and the area is directly related to phi, flux, by the definition of flux. I is directly related to I, and then all the geometry of how the motor was made, this L, whatever, that's all absorbed into K here. So I hope you can see that this phi I is proportional to torque via Bill's law or the Lorentz force. Maybe I should put that here, Lorentz force, right? It's the same thing, okay? K is actually a motor constant. It's a unitless number. Okay, here's a little mini proof of why K is unitless. So you could actually plug in the units. So you have a Weber here, you have an amp here, and you have a Newton meter here. We know this is a joule. A newton meter is equivalent to a joule. A Weber is equivalent to a volt second. And if I start crunching this away, I see an amp is a coulomb per second. The seconds cancel. A volt is a joule per coulomb. The coulombs cancel. And I get joules per joule. Like if I divide this over, is this constant K, and it's unitless. Again, you know, maybe something you don't need to do, but for those that are curious, it's just nice to be able to show yourself that the units cancel whenever you get these kind of equations, right? It's just a comfort, you know. Okay, so we have our Bill's law or torque developed or Lorentz force equation. Okay, so I would prefer that you call this either Bill's law or Lorentz force, because that's really where it's coming from. Okay. So what about the next equation here? We just already talked about it. Great. This is EA equals K phi omega M. This is the back EMF. So it's that back EMF voltage is proportional to the speed and the flux. Perfect. That's exactly coming from that first page over here. That's this, right? Notice phi, well, phi, BA, good. Omega, omega, great. EA, that's another symbol that we use for voltage, phi induced. Perfect. So back EMF voltage, this is Faraday's law, right? And it's actually the same K as the previous K, and it's also unitless. So whatever number you found for one, it works here. That's kind of nice, okay? And here again is just another simple proof. Well, if we relate it in voltage and Webers and radians per second, do we still get K as unitless? We sure do. And you can see it here. Weber is a volt second, radians per second, seconds cancel. I have a volt and a volt, they cancel, boom, K is unitless. Okay. I know this was a heavy lecture. I know there was a lot of material on this, but I hope this gives us some perspective on the AC voltage that's generated in a DC generator when there's no commutator, and how it's rectified with the commutator, and how the internal mechanics of a DC brushed motor work, right? And why the commutator is so necessary in a DC brush motor, right? It's necessary both for generation and for motion when I apply electrical energy to it. All right, I will see you in class, and I hope you enjoyed this lecture. Okay, see ya.